We'll continue now, having dealt with algebraic equation models, and talk about solving differential equations in various forms. We'll start and classify two types of solutions. They're shown here on this slide. The first one is where we have a derivative and then a function of only the independent variable. And we want to solve that differential equation by integrating it from some initial value of the dependent variable to some final value. And to get that result, we have to carry out this integral. And this is called a separable problem. And one way of thinking of this is it calls for finding the area under the f of t curve from t0 to tf. That is also called quadrature, and it requires a separate set of methods to carry out that calculation. And then in the more general case, we have a differential equation where the function involves both the independent and the dependent variable, and we bring to bear different numerical methods to solve that type of an equation. So let's take a look at a quick example of the first type, quadrature, over with MATLAB here. And this is going to be a very simple example where I'm going to define an anonymous function in a little different way than we've done before. So I start with identifying the variable of the function, which is t. And then here I'm going to just put in the simple formula for the function, which is t times cosine of t. Since our methods are likely to evaluate this function with arrays of the value t, we need to be careful to use our dot operator in front of the multiply operator there. And then we're going to say that y is equal to, using the built-in function integral of int fun, and we'll say take it from 0 to pi over 2. Okay? So it's going to integrate this function of t from 0 to pi over 2. And let me save that. I'll just call it integral example. And we'll try to run it. Come over to our command window. And there is the result that we get to 4 significant figures, 0.5708. So that's a very simple illustration. And as usual, if you want to know the numerical methods involved, you can go up to the little help window and put in integral. And the first item here is numerical integration, and it gives you the basis for using the function, a number of different examples, and usually somewhere toward the bottom here. A lot of information here. It gives you a reference as to what method is used and where you can find that in the literature. So that is a very simple example of doing a quadrature or integration of an analytical function. And we can come back and do something that is a little more sophisticated here. Let's go back to the editor and develop a new example where we will read in the function. Looks like I don't have it here, so I'm going to have to make it. Function FC equals STD-NORMDENS of Z. Right. Let's check and see if I've got that standard norm density function available. I think it may be down there. There it is. Okay, so what we're doing here is we are putting in the density function for the standard normal distribution. Now, areas under the standard normal distribution curve are probabilities, and to find those probabilities, we have to carry out an integration of this function between two limits of the standard normal variable z. It turns out that there is no analytical solution to this integral, so this has to be carried out numerically, or in an old-fashioned way, has to be looked up in tables, for instance, at the back of standard statistics texts. So having this, what we want to do is work with this and carry out quadratures to determine different probabilities. So let's see how we do that. We'll open another file called STD-NORMCUMPROB, Standard Normal Cumulative Probability. And so here what we're doing is we create an array of values in A, 100 values between -5 and 5. And then we get the length of A, which should be 100. And then we carry out a for loop from 1 to n. And for each I, which will be each value of A in the array, we determine the integral from using symbol minus infinity up to A. Minus infinity for MATLAB means a very small number. And so what we're doing here is we're finding all the cumulative probabilities for values of A from -5 to 5. And then when we get that in the array P, we're going to make a plot of it and add a grid and some titles. So let's see what that looks like. And this is the typical cumulative probability curve, which is like a sigmoid or S curve for the standard normal distribution. And you can see why we went from -5 to 5, because at -5, the cumulative probability is very close to 0. And then after you get past 4, towards +5, it's equal to 1. So all the action of the function occurs in between. And these are the cumulative areas as we go across the bell curve, the standard normal density. So this shows you, again, how we can use the integral function in order to find the area under, or the quadrature of, analytical functions, in this case, such as the standard normal density function. Now there's another type of quadrature that we have to do frequently, and that is where we do not have a function that we're integrating, but we have instead data. So let's show you an example of that. I'm going to bring up an example called trap Z. Again, not too many statements, but they would be a bit tedious to enter because of the data we're entering. So we have a set of data of a value y versus a value t, and we want to estimate the area under that curve. And the simple function that MATLAB presents, in fact, it's simple enough that we could program it ourselves, is to add up the areas of the trapezoids which occur under adjacent pairs of the data. And that's what the trap Z function does. And then we're displaying it as int y, and we're making a plot of the data just so we know what we're dealing with. So this uses trap Z, which is sort of the alternate to integral, where integral requires an analytical function to integrate, and trap Z wants a set of data. So let's run that. This displays the function that we're integrating, getting the area under this function, and it does so by computing the area under each trapezoidal panel and then adding up those areas to get the estimate. Okay? And then if we go over to our command window, we can see that it gives us a result here of about 571. Okay? So there's your example of using trap Z, and that can come in handy at times. So let's go back to our slides and review this, and then we'll move on to solving general single ordinary differential equations. So this shows you how we illustrated the first use of the integral function, and we did so with a slightly different use of the anonymous function definition, where instead of putting in another function here, we put in the actual formula that corresponds to the function of t. And this is, if you're familiar with Python, this is very similar to what is called a lambda function in Python. And then we integrate that from between 0 and pi over 2, and we get our result of 0.5708. All right, so that is an illustration of that. And then we moved on and we did our example of the standard normal density. And here we show that formula laid out in algebraic form, and it corresponds to the rate of change of probability with the standard normal variable. So the probability from minus infinity to a is the integral from minus infinity up to a of this particular function. And that's what we accomplished here. We also note toward the bottom here that this is handled automatically with a MATLAB function called CDF, which is available from the statistics toolbox, although we don't illustrate that here. And then we went on and took a look at our example with a set of data and finding the area under those data using trapezoidal rule. There are more sophisticated ways of carrying out that integral where you allow for more curvature between the data points, and also even if the data points are noisy, where you smooth out the noise from the data points, but we don't go into that here. Okay, so let's move on to solving single differential equations. And We point out the second example, the example we have here, and then the initial an example, which is sort of a famous example because it turns out that it's very difficult to solve numerically, and we'll see that in a moment. And it turns out that it's a good comparison because we happen to be able to solve this analytically, and the solution is a parabola in terms of the independent variable. So the comments over here to the right are important. MATLAB, one of MATLAB's strong suits is its ability to solve ordinary differential equations. And it has a family of functions that are set up to do this, from simple to more sophisticated. Two of the most common we use are ODE 45, and we use that most of the time. And then another one is ODE 15S, which uses a different type of approach to solution, and it is well suited for what are called stiff differential equations. And it describes there what we mean by stiff differential equations. And you can actually get some help from MATLAB if you go into their help window and put in choose an ODE solver. We will illustrate both ODE 45 and ODE 15S here. It's also possible, although we don't go into it, to program your own function to solve differential equations by a very simple method, such as the Euler method, but we just don't take the time to do that with you here. So what we're going to do is go over and show you how we set up the solution of this equation using ODE 45. So let's go back to the editor, drop out a couple of these functions, and open a function called parasite. Not parasite 1, but parasite. There it is. Okay, so let's take a look at this. We have our initial condition, 0.08. We establish a range of t-values where we would like to see the solution, and we're going from 0 to 5 in steps of 0.1. So that's 50 points we want to see. And then we devise an anonymous function, which is 5y minus t squared. Notice the use of the dot operator there for the squared. And then we call ODE 45 with our function the time values where we want to see the solution and the initial value. In addition to this, we also calculate the analytical solution for each of our 50 values, and then we plot both the analytical and the numerical solution with a grid and titles, etc. And we expect, if we have an accurate numerical solution, that it will lie on top of the known analytical solution. So this is just an example in that way. So we run this, and we note that the analytical solution is coded in red dashed line, and on the scale we have, it just lies along the bottom axis here, because the numerical solution goes up to 300,000 at t equals 5. And the actual analytical solution at t equals 5 is about 27. So obviously the numerical solution has run into a problem here, and a reason for this is because of the nature of this equation, which is called a parasitic equation, and it has a part of the solution sort of hiding in the background, which is an exploding exponential. And we won't go into too much analytical detail to describe that here. So what we're going to do is we're going to make a change in how we call ODE 45. And so let's look at that by opening up a function called parasite1. And the change that we have done here is that we have set a couple of parameters to require ODE 45 to meet much more stringent error criteria as it goes through the solution. In fact, very stringent. So the front end here is exactly the same, but then we create an options variable using the ODE set function, where we set two tolerances, relative and absolute, to values of 1 times 10 to the minus 12. And then we adjoin options to ODE 45 as the last argument. And then after that, we have the exact same statements here. So we carry this out. And here, now what we see is that the analytical and numerical solutions lie directly on top of each other. The thing to keep in mind here when we go about solving a set of, or a differential equation or a set of differential equations numerically, is we also always have to keep in mind whether those solutions are accurate or not. And one practical way to check that is to let ODE 45 solve the equations in a standard way and then set up solving them with a much tighter error tolerance and make sure that those two yield the same solution, in which case you can go back to the simpler ODE 45 and use it. You always need to be a little bit concerned about the numerical accuracy when we're solving differential equations. Okay, so let's go back over to our slides and look at our first solution just using ODE 45 simply, and we see here that it blows up. And then we look at the second solution where we put in the tight error tolerances, and we see that it solved the equation adequately with very little error. Okay? So now we're going to move on and look at more of a chemical engineering example from reactors and reaction kinetics, and that is denoted here. It is a fairly simple example, which we will expand later on. And we have two reactants combining to form a product C with a given isothermal rate of lowercase k. And so we can model the disappearance of the one ingredient A if we have a simple second order reaction as minus k times the concentration of A and the concentration of B. And then we have initial conditions with an initial value for A, for B, and for C, whereas if we start out with no product, that this will typically be 0. And we have a value for K. This happens to be for a reaction taken from the literature. We have a value for K in terms of concentration units of moles per liter and time units of minutes. And then we have initial conditions for the concentration of A and concentration of B being 1/3 that and C being 0. And knowing that we can always get the concentrations of B and C, knowing the concentration of A at any time the initial concentration of A and the initial concentrations of B, and that's from simple stoichiometry. Now, as we set up the solution of differential equations, it's useful, something that I recommend, that you create a diagram to represent the solution to make sure that everything hangs together and you have the information and equations that you need. And this is one such diagram. It's called an information flow diagram, and it starts in the middle by describing the differential equation you're solving, and then we note that there is a constant parameter k that has to be provided. And then we use a numerical method starting with initial value of CA0 to solve for a value of CA, usually in a little bit after time equals 0. And then we can use that value in the stoichiometry to solve for CB and CC given their initial conditions. And then the CB provided here and the CA provided here gives us the information we need to move on to the next step of time. And the numerical method that we use is denoted in this left-facing triangle, okay? So now what we want to see is how we go about doing that with MATLAB and with the ODE 45 routine. So let's come back to our editor and let's bring up a file called batch. This is a function that computes our derivative. It has time and the current concentration of A, and then it has 3 extra parameters that it needs to carry out these calculations to compute the derivative of A. And so it's setting up one of these functions again where we need to pass through some extra parameter values, and you've seen us do that before with algebraic equations. You'll see it again here. So let us open a function called solve batch reactor. And here we have it. So we set our basic data, the rate constant, use some comments here to indicate units, our initial values of CA and CB, and the CC value is 0. Set up a solution span, which is 0 to 20 minutes, in steps of 0.1 minutes, so that's about 200 points of a solution. Create an anonymous function. Now, here we go back to using a subservient function to complete the anonymous function, and we note that the key arguments for ODE 45 are T and CA, but we have these 3 additional arguments, K, CA naught, and CB naught, that we need to pass through to the batch function. So then we create ODE 45, and the results are the T values in T-span and the corresponding concentrations for each one of those T values. And here we put in our anonymous function, T-span, and the initial condition for A. Excuse me. Once we have the solution for CA, we can calculate CB and CC from the simple stoichiometric relationships. Here you'll note that we're doing this for a whole array of the CA solutions. And then we create a plot with 3 curves showing CA, CB, and CC. And if I would like down here, I can add something to this and put in a legend, and we can call this first one CA, the second one CB, the third one CC. Just add that as a feature. Save this and try to run this. And there is our solution. So the legend sort of helps us here identify the curves. But what we see is that we deplete our concentration of A a certain amount. We deplete the B completely. It's actually considered an initiator for this reaction system. And we produce a certain amount of our product as we go on. And most of the reaction is complete in the first 20 minutes. So that illustrates how we can go about solving this. And you'll notice that we have three variables of interest here, CA, CB, and CC. We only have one differential equation, that for CA, and we get the CB and CC values over here by using stoichiometry to convert the results. Now, there is another way to go about doing this, and that is to use what is called the differential algebraic equation approach, DAE, and we can illustrate that by coming back here and opening a file which is called batch DAE. And this looks somewhat different in that in addition to describing our differential equation for CA, we also describe our stoichiometric results as algebraic functions that at all times must be equal to zero. In other words, as we go along solving the differential equation, these two algebraic equations need to be solved at all instances of time. So it turns out that MATLAB has a neat way of solving this type of a system called a DAE. And you'll notice once we compute our three outs, we transpose that to the out variable, which includes the differential equation rate of change plus the results of our two algebraic equations. And so let us take a look at how we go about solving that, because it's a different approach. And so we'll open a routine called solve batch DAE, solve batch reactor DAE. And you can tell right away that it's more involved because the statements don't fit on one screen. But there are a lot of comments too to help show you how to set this up. And the first four statements here are identical to what we had before, plus the t-span shown here is the same that we had before. But then things change because we set up what is called a mass matrix, here denoted as capital M. And in this case, we have three differential algebraic equations. We set them up. We set up a mass matrix where if we have a 1 on the diagonal, it indicates that that equation is differential. And if we do not, if we have a 0, it indicates that that equation is algebraic. So you'll recall back over in the batch DAE routine that our first equation was differential, second and third were algebraic. So this is how we set up the signal for that. And then we create initial values for each one of these, all right? And then we use an option statement with ODE set where we indicate that the mass matrix is identified as M, all right? And then the final step here, which is required, is that we have to use a different integrator function, in this case ODE 15S, which accommodates the use of algebraic equations in addition to differential equations. So we have our anonymous function just as before, and then we have our t-span y, and we now include our options ODE set results. When we have our results in the end, the y solution now includes all three variables, a, b, and c, and so we unpack those into more familiar variables, carry out our plot just as before, all right? So that's the difference. You can tell that it's a little more complicated, but it turns out that in many of the systems that we model, especially more complicated chemical reaction systems or reactor models, this is an efficient way to go about solving them. So let's run this, and we get the same result that we got before, okay? So that is the story for solving a single set of differential equations or a single differential equation with adjoined algebraic equations. We've illustrated both of those. So let's go back to our slides, come back around here. And this corresponds to the first way that we did it, where we only include in our batch function the derivative here, and then we solve for that, but at the end we unpack the CA solution into CB and CC solutions using the reaction stoichiometry and carry out our plot. And then for the DAE approach, we now include the two algebraic equations set equal to 0 and assigned to out 2 and out 3. And here we unpack all three in order to do these three statements and return the out variable. And then this shows the addition of the mass matrix and the ODE set, and then solving it with ODE 15S. And we come back and we have the same solution that we had before. Okay? So now what we want to take a look at is we want to move into the area where we're solving more than one differential equation. And we'll start that with a simple example, and then we'll move on to an example which is the expanded reaction system that we were modeling here, where it actually has 6 components and not 3. So let's pop back over to our editor. And let's take out a few of these things to make room on the tabs up here. And we'll open a function called derivs.m, RIVS. And so we could have typed this in, but it just saves a little bit of time to show it to you. So we have two differential equations, and they're mathematical. They're not modeling any particular physical system. And we take in t and the current values of our dependent variables. And then you'll notice what we do is we make reference to x sub 1 and x sub 2 to compute the derivatives dx1 and dx2, transpose that, and send it back. One thing you'll notice as you look carefully here is that when we get into an operation like exponentiation to 2, squaring, where this x might turn out to be an array of values of x, we use the dot operator, and we also use it down here in front of this exponentiation to 2. Okay, so these specify our derivatives, and then we want to take a look at how we go about solving this. So we're going to open a file called solve multiple ODEs. There it is. So here we start with initial values for our x's. And you'll notice that as we did this, we transposed the initial values. And because we did that, we transpose, whoops, wrong ones. Yeah, we transpose the derivatives in order, let's get rid of this, to have it be a column vector for each one of those. And here we set up the solution from 0 to 5 in steps of 0.1. And we call ODE 45 with our derivatives function, our span of results that we want, and our initial conditions. We get to the end and we plot our results. And then we can run this. And this shows the results of solving those two equations simultaneously, right? And they start with initial conditions of 2 and 0, and they converge upon constant common values of 1 as time approaches 5. So this shows you the solution of two simultaneous and interconnected differential equations where the x2 appears in the derivative of x1 and vice versa, okay? So let's come back to our slides and just take a look at that one slide, which illustrates what the equations look like in algebraic form, and then how that translated over to our code, and then what the solution code is below, all right? Good. So let's come back to our batch reactor model and expand it some. And here we provide the actual literature documentation of these reactions. And you might wonder, well, why did you use the letters A, B, C, etc.? Well, one of the components down here, 135 tricarbonmethoxybenzene, all right? So we think it's a little simpler just to refer to that as component A. Wouldn't you agree? So now what we're dealing with is the real reaction system. And we have 3 simultaneous chemical reactions, all with A, but A and B provide C and a byproduct F, and then C recombines with A to provide D, and again, byproduct F. D combines again with A to provide E, and again, another molecule of F. So this is the real system. So what we want to do is develop a set of equations for the disappearance or appearance of each one of these components. And the disappearance of A is somewhat similar to what we had before with the first reaction, but now we've got the second reaction and the third reaction, and we have the same initial concentration and the same value for K1, but now we have values for K2 and K3, and these are taken from the literature. And then the disappearance of B is just the first reaction. For the disappearance of C, we have a positive, which means C is being produced by the first reaction and depleted by the second. And for D, we have it's being produced by the second reaction and depleted by the third. And it turns out, with a little bit of work, you can describe the concentration of E by stoichiometry with this expression, and the amount of F that you have is equal to the amount of A that has disappeared. So you can use stoichiometry for E and F. So we have a more complex system here, and as these systems become more complicated, the use of the information flow diagram becomes more helpful. So here it is for these 3 reactions, and the basic idea is that we write down the differential equations that we have, and then that we are able to integrate stepwise each of these. And then we need to say, where does the information come from that allows us to complete these derivative expressions? And we don't show it here, but the constant parameters K1, K2, and K3 appear in various places. And then we can show that what's required to compute E, given the values of A, C, and D coming back, and then what's for F. And then once we have those, we've got the solution. And then it shows how all of these feed back into here to complete our expressions for the derivatives. And the expression that you might want to use here is that it appears that the information hangs all together and we're not left wondering where some piece of information comes from in order to formulate the derivatives. So this is very helpful and of course never required of you, but I really think that as you're modeling a system, whether it's a reaction system or other, it's very useful in organizing the solution. So let us come back over and look at how we formulate the derivatives for the solution of this system. And that is in a script called multibatch. So here it is. So what we have, and this again is typical, is we have our independent and our dependent variable. In this case, we've got 6 different independent variables, A, B, C, D, E, F. And then we have, for the first 4, A, B, C, D, we have the differential equations. We unpack it here into our common variables, make it more easily understood. And then the last 2 represent the stoichiometric relationships set equal to 0 by shifting things to the left side of the equal sign. And so we have 4 differential equations and 2 algebraic equations. And then this is set up now for solving as a DAE system, all right? So we'll open up a script called solve multi-batch DAE down here. And this is the script for solving the equations. Again, set up quite logically. Start with our basic data of our rate constants, and then our initial conditions, and then putting those initial conditions into a y0 vector, transposing it here. And then we're saying that we want to solve this system from 0 to 500 minutes. And you'll notice that the first solution we did, just A plus B going to C, we only solved that for the first 20 minutes. So there's evidently more going on here. And then our mass matrix now contains 4 ones on the diagonal because we have 4 differential equations, and then 2 zeros for our 2 algebraic equations, the stoichiometric relationships over here. The rest of this is set up quite similarly, with the ODE set of M being the mass matrix, set up an anonymous function, T and Y, where we add the arguments K1, 2, K3, and the initial value for A, all right? And then we ask ODE 15S, we need that because we're doing a DAE, to solve this in the same way we did before. We unpack the solution into our 6 variable names, and then create a more extensive plot of all 6 of them, all right, and include a legend. And then you'll notice we elaborated a little more on the legend here. where we determined where we would like the legend to be located on the plot, and we say that it wants to be in the northeast of the plot, upper right-hand corner, and we would like it to be outside the plot. So we're able to do things like that, add labels and title, and we can run this, get this plot, all right? And it includes all the colors for our different constituents. This is the outside the plot legend. One thing you'll notice is there is a red line here for B, and that is our B initiator, which disappeared in our initial simulation after 20 minutes, but it essentially kicks off the reaction, and we have C coming up, peaking out, and then we have D coming up, peaking out, and then we have E gradually increasing, and F, which is probably a byproduct that we're going to have to separate out, which just keeps increasing because it's produced by each reaction. So this is a good example of taking it a little bit further, all right, and solving it as a DAE. So let's come back to our slides and summarize that, and then we're going to move on and take a look at a different type of differential equation with what we call split boundary value characteristics. So let's come back to our slides. It shows here the additional arguments that we had because we use A0, initial value of A, in our stoichiometric relationships, and we need all three Ks, right? And so that is that, 4 ODEs and 2 algebraic equations. And then this is the start of the script to solve this, noting the use of the mass matrix. And one common thing I want to mention, just because of what I've observed of students, is that if you are not solving a DAE, if you do not have algebraic equations coupled with your differential equations, you do not need the mass matrix, and you do not necessarily need to solve the equations with ODE 15S, okay? So that's just something to mention because I've observed students trying to do this when they didn't need to, all right? So that is that. This is the final part of that, unpacking the solution and preparing the plot. And then this is the plot, okay? So we're going to move on and deal with the final type of example that we have. This will illustrate it. And first, it's showing us how we can deal with a second order ordinary differential equation. And in this case, we have one with what are called a split boundary condition. So since it's a second order equation in one dependent variable, let's come back here, it needs to have two initial conditions or two conditions in order to solve it. It could have an initial value of y and an initial value of the derivative of y, which would make it what is called an initial value problem. But in this case, we have said we want the initial value of y to be 5 and the final to be 8 over a range of 0 to 10. So y at 10 is equal to 8. So first, the technique which is general to solving a second order differential equation is to decompose it into two first order differential equations. Now, in chemical engineering modeling, we don't often see model equations with derivatives higher than second order. In civil engineering, in structures, and sometimes in mechanical engineering, they see systems which have third and fourth order derivatives, but we generally don't. But the idea here is we decompose it first by taking our dy dt and creating a new variable y1. Now that sets up a differential equation that says dy by dt is equal to y1. And then for this differential equation, we merely substitute y1 in here. So dy1 dt, which is this second derivative now in terms of a first derivative, is equal to a quarter of y1 plus y. Now, the next thing is we need a strategy to solve this, and a typical strategy numerically is that in order to do this, we need an initial value for y1. We don't have one. So what we do is we estimate one, and we solve the equations out to t equals 10. When we get there, we check and see if y is equal to 8 when we get there. And if it's not, we come back and change the initial value of y1 until that occurs, all right? So it's called a shooting strategy. We're shooting at the end target and we're missing it, and we're adjusting the angle of the shot in order to eventually get it to converge. So let's see how we can set that up. Let's go back over to our editor and take out a couple of these. We're done with them. And we'll open a file which is called diffeqs. And this corresponds to what we had for our two ordinary single order differential equations in terms of y and y1. In this case, y sub 2 here is equal to ry1, and y sub 1 is equal to ry. So this is how we compute our derivatives. That's very simple. And then we'll open a file called split boundary. Again, not too many statements. It's starting with an initial value of 5 for y, and we're estimating the derivative to start with at minus 4.4. And note the use of the transpose here. And then the t-span is we're going from 0 to 10 in steps of 0.1. And we're asking ODE 45 to solve these and to produce our results, and then we're plotting them. And we note that what we're doing here is we're plotting all rows of the first column, and the first column corresponds to our y, all right? So as we run this, and you know that we want y to be equal to 8 at the final value. So we do this. And what we notice here is that y is equal to somewhere between 5 and 600 at t equals 10. So obviously, the initial guess for the derivative of minus 4.4 doesn't get the job done. Now, we could sit here and we could experiment manually with different values of this, but what we do at this point is we come in and we say, we know the end condition needs to be 8, so we need to adjust this value to get a target of 8 for the final value. And it turns out that we can go back to what we did for algebraic equations, and we can couple in our f0 function to help solve this problem. So we're going to go to split boundary M. Solve split boundary M, I'm sorry. So what we notice here is that we're now incorporating f0 to solve the relationship split boundary 1 with an initial guess of minus 4.4, right? And what is split boundary 1? Well, let's take a look at it. It is a function that solves the differential equations for an initial guess for the derivative of y 1, 0, and an initial value of y of 5, which we know, from 0 to 10, solves the differential equations, and then returns the difference between the last value of the solution. Notice the use of the keyword end here, all right? Last row, first column, minus 8. So it's trying to drive this to 0, all right, by adjusting the initial derivative value. So if we come back here, and then it's going to make a plot of the result. So if we come back here and run this, there is the solution. And you'll notice it starts at 5, takes a dive, almost to 0, and then ends up precisely at 8. Okay? Now this is a very touchy solution because I think, let's see if we display that. Command window. Yeah, here it is. Our solution is minus 4.4137 and many more digits. And you'll notice that it is very close to where we started with minus 4.4, and it blew way up. So this is a very touchy solution, but it was able to solve it for us and provide us with an accurate 2-point boundary value solution. So this technique is one that you will see quite frequently when you have what we call split boundary value or 2-point boundary value problems, where you have differential equations where you don't have all the initial values that you need, but you do have values at the end that you need to match. All right, so let's go on and look at a final example here, which is a little more involved, but it's more relevant in terms of engineering, and that will bring this particular screencast to a close. So this is what we found with our first solution, where it ended up with a huge final value, and it needs to be down here somewhere at 8. And then we incorporated F0. We incorporated F0 in order to solve this using our split boundary volume 1, which is shown here. And that solved the differential equations and compares the last value to 8. All right, so that's what we showed you. Now we're going to move on to an example that's a little more engineering oriented and more detailed. And that is an example from heat transfer, where we have a countercurrent tube-in-tube or pipe-in-pipe heat exchanger, where we have a cold fluid running from left to right in the inside, and on the shell we have a hot fluid moving from right to left. And so here we have two differential equations, which for our purposes here are actually quite simple. They're linear coupled differential equations, but what we have for specifications is that we know the inlet temperature here, and we know the inlet temperature of the hot fluid here. So this becomes an end condition that we have to match. Also, we have constant parameters like mass flow rates, heat capacities, and inside and outside heat transfer coefficients, which are related by this geometric relationship. And then just for the record, I've included a nomenclature slide which gives you all the definitions of the nomenclature that were used in that particular model. So we've summarized again here our equations, and we've noticed here that we have an initial value for Tc, cold, and we have a final value for T, hot. So similar to our last example, in order to solve these, what we do is we start and we guess the outlet temperature for the hot stream, which occurs at Z equals 0. We have the inlet temperature for the cold stream. We integrate this through across the length of the heat exchanger, and we end up getting a value of the hot stream at the inlet temperature, and we have to compare it to what the correct value is, come back and adjust our guess for the outlet hot stream until these match. So it's a similar situation that we just illustrated. It's just a little more involved. So we come on and we develop an example with basic data and operating conditions. So we've got essentially a 1-inch tube inside of a 2-inch tube. And these are standard gauge tubes, which means standard thickness. And we give what the outside, inside diameters are. We're taking this as 5 meters long, all right? Which would be between 16 and 17 feet, if you like feet. And then we have our operating conditions of the hot stream coming in at 50, the cold at 10. We're dealing with water at this at an average temperature and a heat capacity value and a flow rate of 1 liter per second, 0.3 liters per second, and we have a heat transfer coefficient given in units of watts per meter squared Kelvin or per meter squared degree C. Okay, so we're going to show you how we go about solving this now, and let's come back over to our editor. Let's take out some of these, and let's open a file called tube-in-tube heat exchanger. All right, should be down here somewhere. Okay. Let's see what we have here. First, we have just dimensional calculations having to do with areas and converting them all over to standard SI units in meters, starting here with the values we had in inches. And then we've got our fluid properties, all right, again, basic data. We've got our heat transfer coefficients. Here our geometric relationship to get HO. Then we have our operating conditions in terms of liters per second, and we take that and convert that over to mass flow rate for each kilograms per second. We have our inlet temperatures, and then we have our span for our solution, which is 0 to L, the length of the heat exchanger, 5 meters. We are estimating the outlet hot temperatures so that we can solve the equations forward. And then when we get to the end, we're going to compare what we get for the hot inlet to the requirement of 50 degrees. So at that point, we set up our initial conditions, our anonymous function, and again here we include a number of these extra parameters to be passed through to our derivative routine, okay? And the heat capacity is the same because it's water and or relatively the same. We solve the equations, unpack the solutions into our cold and hot profiles, and plot them, right? Now, what we were making use of here was a function to compute the derivatives, HTEXR. So let's open that. And so this is fairly simple, but you'll notice it includes these additional parameters that we put in our anonymous function. We unpack T to get TC and TH, compute our derivatives, assemble them into an array, and transpose them so we get columns. And again, that comes back to our initial conditions being transposed, all right, that you can see here. And then that is what is used for the solution. So when we run this, I think I ran that, didn't I? Yeah, it just didn't show the graph. So this is what we've got for the cold and the hot stream from 0 to 5 meters. And you'll notice that we started with 40, and our inlet hot that it's getting is about 52 degrees. And the specification is that it needs to be 50 degrees, which is the true inlet hot temperature. So at that point, what we do is we use the same approach that we used for the simpler problem with the 2-point boundary value problem. And we want to use F0 to adjust our initial estimate here, hot water out, so that we get 50 precisely for our hot water in. Okay? So let's get rid of this chart and come back and open a file, which is called tube-in-tube heat exchanger F0, I think. Here it is. And so here, much of the front end is exactly the same, all right? And you'll notice, as I've gone through some of these examples, I've been pretty careful, especially when I'm doing units conversion, to put in the units as I go along, because when you end up with results that don't look right, quite often it has to do with a mistake in units or units conversions, and it's good to have these comments here to go through and troubleshoot that. So this is all the same, all right? And then we have our solve ODEs function with all of these parameters. The only one that's really important for F0 is the first one, which is our estimate of the hot water out temperature. And then all the rest of these are going to be passed through F0 to our solve ODEs function. So F0, solve ODEs anon with TH0, and starting with 40 as our initial guess. And so it's going to do that. So let's take a look at solve ODEs. So what this does is it solves the differential equations just as we did for a specific initial estimate coming in here of TH0, solves for it, and then gets the last value of the hot, that's column 2, and compares it to THI, which came through up here, and THI is 50 degrees. So it wants to, F0 wants to continue to adjust TH0, solve the equations until this goes to 0, which means the last value of the hot is going to be equal to our specified inlet temperature. So that's the way we want this to work, all right? So what we will do is come back over here and see what happens as we go down here. It solves for this, all right? And then to complete the picture, now that we have the right value of TH0, we go through and solve the equations again here to get the correct profiles, unpack the solutions, and create a plot, all right? So that's how we go about doing this. And let's run this. And this is the solution. And you'll notice now it doesn't start it quite at 40 degrees. It's lowered it down to 39-ish. And it's hitting our target exactly of 50 degrees at Z equal 5 meters. And 50 degrees is our specified inlet temperature of hot water. Okay? So that is the example, is the last example that we're going to do for this segment of the screencast for MATLAB Bootcamp 2. So let's come back to our slides and finish up. Just documenting what our various specifications were, and where we started this was with an initial guess for the hot outlet temperature of 40, and then going through and solving the equations with our HTEXR, defining the derivatives. And then this is what we got, and it didn't quite meet our 50 degrees C requirement. So we came back, same front end, but now we're using F0 to adjust our initial, to adjust our initial estimate of the hot water outlet temperature and do the solve ODEs to drive that equal to, so we get an inlet hot temperature at the end of the exchanger, which is equal to the spec. And then we come through, solve them again, and create our plot. This is the solve ODEs, and again, it shows that it's THO, that it's adjusting until we get the final solution equal to the specification of 50 degrees. And then this is what we get. And also over in the command window, we display what that final outlet temperature of the hot water is, which is about 38.8 degrees Celsius, and you can see that on the figure. All right, so that's it. We're going to call this to a close, and then we'll come back with a third screencast for Module 2, which is going to deal with optimization calculations and then curve fitting or regression calculations, which also represent a type of optimization calculation in applied statistics. So that's it for now. We'll see you later.